Welcome to this explainer. Today, we're taking a virtual factory tour to demystify something that honestly seems almost like magic. We're going to look at how completely invisible gases are transformed into the solid plastics we use literally every single day.
It's a fascinating question, right? I mean, how exactly do we take a gaseous molecule, just floating around in the air, and engineer it into something like a rigid fuel tank or a super stretchy piece of food packaging? Well, the answer doesn't lie in magic, but in some truly brilliant chemical engineering that we're about to uncover together. Okay, let's dive into our roadmap for today. First up, welcome to the plastic world. Second, engineering high-density polyethylene. Third, mapping the Ziegler process. Fourth, linear low-density polyethylene. Fifth, the unipole gas phase process. And finally, from molecules to materials. Let's get to it.
Section 1. Welcome to the plastic world, the polyethylene foundation.
So polyethylene is the most widely produced plastic in the world. We're talking tens of millions of tons manufactured globally every single year. But it comes in very different structural forms depending on exactly how we make it. On one hand, we've got high-density polyethylene, or HDPE. It has this strictly linear structure with almost no branching. Because those molecules can pack so tightly together, it's very dense, ranging from 0.94 to 0.97 grams per cubic centimeter, and it's highly rigid. Now, on the other hand, we have linear low-density polyethylene, or LLDPE. This one has a linear backbone too, but it features these short, uniform branches. Think of those branches like little molecular spacers. They make the material flexible without the polymer chains getting impossibly tangled up. And to get these vastly different physical properties, well, we need entirely different factory processes.
Which brings us to Section 2, engineering high-density polyethylene and the need for rigidity.
Okay, the absolute magic term for HDPE production is slurry polymerization. See, when you chain ethylene molecules together to make a solid polymer, the reaction is highly exothermic. Basically, it releases a massive amount of heat. Slurry polymerization solves this by conducting the reaction inside an inert liquid hydrocarbon solvent. Now, this liquid doesn't react with the chemicals at all. Its sole job is to safely absorb and dissipate all that excess heat. This keeps the reaction perfectly under control, all while the solid polymer forms a suspension, or a slurry, right there within it. Moving right along to Section 3, mapping the Ziegler process inside the HDPE factory. If we map out the flow of the Ziegler process starting from the top left, we can see where the raw ingredients, the metal alkyl and the ethylene gas, are introduced right alongside that hydrocarbon solvent. They flow straight down into the central polymerization reactor. It's inside this exact vessel that the gas actually turns into a solid, suspended right within the liquid solvent. Let's break those steps down a bit more. Inside that main reactor, the temperature is carefully maintained between 100 and 130 degrees Celsius, at a pressure of about 1 to 20 atmospheres. That's where the slurry polymerization happens, but, we can't just stop there. The liquid solvent carries this newly formed solid polymer slurry down into a catalyst decomposition vessel. Here, the catalyst gets completely deactivated, usually by adding an alcohol. Finally, the whole mixture moves over to the purification stage. That's where the solvent is extracted, filtered, and actually recycled, leaving just the pure polymer behind to be dried and extruded. But honestly, the real unsung hero of this entire operation is the Ziegler nano-catalyst. This is a very specific chemical recipe, often a mix of titanium tetrachloride and an aluminum alkyl. This organometallic compound doesn't just kick off the reaction, it strictly coordinates it. It essentially acts like a microscopic traffic cop, forcing every single ethylene molecule to line up perfectly straight. And that lack of branching? That is exactly what gives HDPE its high crystallinity and its legendary toughness.
Let's shift gears now for Section 4, linear low-density polyethylene, the need for flexibility.
Now, the key to this material is beautifully summarized in our sources. It says the structure of LLDPE has a linear backbone with short, uniform branches able to slide against each other upon elongation without becoming entangled. So by introducing comonomers into the mix, things like 1-butene or 1-hexene, engineers literally force the creation of these short branches. They essentially act as molecular shock absorbers, which is what allows the plastic to stretch and bend so freely.
All right, Section 5, the unipole gas phase process, revolutionizing LLDPE.
Now, looking at the layout for the unipole process, what's really fascinating here is what is fundamentally missing. There is absolutely no liquid solvent
anywhere in this system. None. Union Carbide developed this back in the late 1970s to be a purely gas phase process, and it was an absolute game changer.
Let me be your tour guide through this continuous loop. Gaseous ethylene and our comonomer are constantly fed into the system, and over on the side, there is a massive blower and a cooler. Now, this loop is absolutely vital. Since there's no liquid to absorb the heat of polymerization this time, this high-speed stream of cooled gas is literally the only thing preventing the temperature from skyrocketing. I mean, if that cooler fails, the polymer would just melt and coagulate into a giant solid block right inside the reactor. Anyway, as the gas circulates, solid plastic particles grow directly on the surfaces of the catalyst grains. Finally, the finished product discharges right at the bottom through a specialized gas lock chamber.
The true heart of this factory is the fluidized bed reactor. And guys, this is sheer engineering genius. The gases are blowing upward from the bottom with such tremendous force that they literally suspend the solid catalyst and the growing polymer particles right in midair. Picture this. You have solid grains of plastic growing up to 1,000 millimeters in size, just floating in a hurricane of reactive gas. It completely eliminates the need for liquid diluents. It's just brilliant.
And that brings us to Section 6, from molecules to materials, putting plastics to work.
To perfectly summarize our journey, let's look at how these methods compare. The liquid slurry of the Ziegler method utilizes strict temperature control and specific catalysts to give us HDPE. Its high tensile strength and rigidity make it perfect for heavy-duty applications. Think irrigation pipes, industrial drums, and automotive fuel tanks. On the flip side, the gas phase unipole method produces LLDPE. Its short molecular branches give it that incredible flexibility needed for things like thin films, shrink wrap, and protective packaging liners.
So, the absolute crucial point here is that chemical engineering isn't just about making a synthetic material. It's about making it efficiently, safely, and specifically tailored to human needs. The Ziegler process relies on liquid solvents to manage heat, while the unipole process completely revolutionized the industry by eliminating those solvents altogether, which, as you can imagine, drastically lowered capital and equipment costs. Yet, both of these methods heavily rely on advanced catalysts to act as molecular architects, dictating the final shape of the polymer.
It really makes you look at the physical world a bit differently, doesn't it? Next time you pick up a rigid plastic drum or stretch a piece of flexible packaging film over your leftovers, take a second to ask yourself, was this object born in a carefully cooled liquid slurry, or was it suspended in a towering hurricane of gas? Thank you so much for joining me on this explainer, and keep questioning the incredible engineering all around you.